Hello, my name is Thales Korting, and in this video I will show again how decision trees algorithm works. I'm calling this part 2 because in the past we already explained it in part 1 the use of the formulas for gain and for the entropy, and how we split the problem in sub-problems in order to classify a specific data set. We are going to use this well-known data set, which is Iris dataset. It is composed by 4 features: the sepal length, sepal width, petal length, petal width, in order to distinguish in 3 classes: setosa, versicolor, virginica. It's important to show that in the scikit-learn library called opendatasets, I have found this dataset with 150 samples. So it is composed by the original samples, and I also created, using noise, 300 in order to have more samples to make the problem easier to visualize in the graphs that I'm going to show later. This is the only reason for which I created these extra samples. This data set is composed by 3 colors or 3 classes: setosa, versicolor, virginica, and I'm using these 3 colors to represent them. And recall that we have 4 features: sepal length, sepal width, petal length, petal width. When we put all the 450 samples and create the histograms, coloring the features with the class names, we will have these 4 distributions that I'm showing here. The idea is that the decision tree algorithm will start with all the data exactly in the way that we have here, and we'll go through every different feature and try to find a threshold, and this threshold will always start from the very beginning here, the minimum value available in this feature, and go up to the maximum value of this feature. Do exactly the same for this, and for this. And we will create a threshold for all the possibilities inside this interval and compute what we call the gain. In this animation, I show exactly this, the threshold for all the 4 features created, and we iterate through the possibilities and compute the actual gain for all these values. What is the aim? The aim is to, by computing all these gains, we can find the maximum value of the gain. In this case, it's easy to understand that these 2 features will be able, with a threshold around here and around here, will be able to distinguish the green class from the 2 others. And in this graph, we can see exactly this. In this case, I just highlighted the higher gain for the 4 thresholds. The higher gain for this feature is here. So we can see that it divides a little bit good the green class from the other 2, but we have a confusion here. The same happens here, and we have a very high gain in this threshold and a very high gain in this threshold. In this case, the algorithm will choose this feature and this threshold to make a split on the data. Let's recall what we do when we mention the gain. The gain for every feature, in this case we have 4 features, is going to be the information value for all the features minus the information value for the 2 nodes provided by a threshold. Threshold will divide the data set in 2 sides. This side will have the information value, and also this side will have the information value. And in this case, the information value for both sides is the entropy. and the formula for the entropy is shown here. It's good to know if we split this data set into parts. Let's show this, for example. We will have the information value for this side and also for this side. It's good in this case that by dividing here, we will maximize the gain because we isolated one feature for the other two. And in this case and also this case, the gain is not so high because with the best threshold, we are not able to divide the data set, isolating one of the classes. And so when we choose this feature and this threshold, the algorithm will create the first division. This petal length with greater than this value, it will represent these two classes. But when it is smaller than this threshold, it will represent the other class, the green one. We can say that we solved the first class, and now our problem continues, but now with only two classes to split. Let's try to find another way to divide this data set, but now using only these two classes. Now we have reduced problem. We can see that we don't have more the green class. We only have the blue and the orange classes. We are going to do exactly the same. It's also easy to know that these two features will not be able to divide the data, and these two ones will divide the data but with some overlapping here and here. Let's show this using our animation that computes the gain for every threshold. We can see that the thresholds in the top of the graph are very low gains. And in these two cases, the gain is much higher. So the algorithm will try to decide for one feature that is going to be chosen for the second branch of the decision tree. I highlight here the highest gain for every one of the four features. We can see that here is not so big, not so big, this is big, and this is bigger. So in this case, the algorithm will choose this feature, the petal width, in order to make a split on the data set. And it's also easy to say when the value is greater than this threshold, we can classify it as the orange class, and when it's not greater or is smaller than the threshold, we still have some confusion, but we have the majority of the blue class. So what we do in this case, we create a second branch in the data, now using the petal width feature. When this feature is greater than this value, we can consider that the orange class or the Virginica class is reached. But in the other case, we still have a confusion that we are going to find a new threshold in order to split them. The last threshold that we have is considering these two classes as well, but you can see that we have only a few elements of the orange class because all the majority of the orange elements were already solved by the previous threshold. When we compute the threshold for this, we can see very low values now because it's more difficult in this case to divide the data, and we can see that the highest threshold in this case will come from this feature, petal length again, and in this region. So by using this threshold, we can split the data in two sets and split all or the majority of the orange values here and the majority of the blue elements here. We can see also that we did not solve it perfectly all the elements, but at some point it's good that we stop to create thresholds in order to avoid the overfitting in our data set, but to create a more or less general model. By using this threshold, we are going to split the data in two more classes. When the petal length feature is greater than this threshold, is the orange class again, and in the other case is in the blue class. So our decision tree is composed by these 3 decisions created by using all the available values and find a threshold that maximizes the gain at every iteration. But the good thing is that when we isolate one class, we can continue to create a different threshold only with the part of the problem. In this case, we reduce the size of our problem, and we can go on by creating new thresholds and to classify our entire dataset with success. Thanks for watching this video. Please go to my GitHub. You are going to find the source code for this video and for the other videos. You are going to find latex equations for the formulas that we use, and also data set that I use in my videos. Sometimes I create the data sets and I make available on my GitHub site. If you like this video, please click on the like button and share this video with your friends, and subscribe to my YouTube channel. Thanks a lot for your attention. This is how decision trees algorithm works. Thank you.